Recording's rolling. It is Thursday, October the 2nd. So today and tomorrow is going to be kind of an open lab type of day. I just gave you guys this page here, which on one side, this is going to be a lab for a Varignon panel. How you guys build, and I'll show you guys what that's about, show you guys a video, what that looks like. And also, you have you guys do spring constants lab, and I'll help you guys out with those two. What have you guys set up a table, solve the spring constants. So you'll have today and tomorrow be pretty open. Just as long as you turn in this page by the weekend, then good to go. I'll get both of these grades in the book, so this will be like 2 separate labs. Okay. Yesterday I gave you guys a dynamic statement quiz, which is due on Monday. And oh yeah, your textbook puzzles also turn in by tomorrow. Actually, some of you guys have already turned these in. You probably haven't finished anyway because I'm just looking for 10 of the textbook puzzles, which we've done at least that many in class. All right, so you guys with the agenda so far over here? All right, so let's do this first. Spring constants. Spring constants. All right, so you guys raise your name on your paper. Okay, now if you flip it over on the backside's blank, so that you guys can draw a table here. Okay, let's call this spring constant lab, and then make a 2-column table. You'll be looking at different springs, or like spring scales. So these right here. And I want to know what is the corresponding spring constant for each one. Okay, that's to say how stiff is the spring and the brown scale and the green scale and so on. Okay. Now altogether there are 6 scales. Maybe do a little scavenger hunt. They're scattered around the lab tables back there. Okay, so if I get the order right here, I think the one with the smallest spring constant is the blue scale. Then it goes green scale. Then it's brown scale right here, brown. Then goes red, white, and gold. Or this was the gold scale, so it's just the stiffest one. So I think I got those in order. Yeah. Okay, so this should be like ascending spring constants. Okay, here's what. Okay, so you have all these spring scales going on. Here's 4 of them right there. 2 other ones. Okay. So I wonder, like, what is the how stiff are these springs? Like here, this green one is not very stiff. See, I put a little force and it stretches really easy. Okay, but this gold one, like, with so much force, and it's really hard to stretch this one. And you can see that too, because the length of the spring scale goes up to 50 newtons. Well, if you measure up to 50 newtons of force, it's 50 newtons of force. All right, guess that. Okay. So, guys, if you know how much the spring can stretch, and you know the corresponding force, and you want to determine how stiff is the spring, called spring constant, what do you apply? Whose law was that? Whose law? Starts with an H.
Paul Hewitt. Paul Hewitt's law.
Yeah, Paul Hewitt's law. Hooke's law. Guys, it's Hooke's law. Okay. Well, we've got a poster we can reach for that. Hooks. Yeah, I got it right here. Okay. Actually, I have 2 posters for this. Do you guys remember this? You put a force on a spring to stretch it stretches something out. And this is linear, so if you put on 3 times the force, so it stretch 3 times as much. You guys remember that? Okay. Now, a lot of textbooks will throw in a negative right here. You guys are talking about the restoring force. So if you stretch the spring to the right, doesn't the spring actually pull back to the left? Okay. So that's the interpretation for the negative. Okay. So however you want to think of this. Okay. So here, actually, this is a good picture anyway. You guys see it's how much it's stretched beyond the unstretched value, or you could have compression, but not so much on these spring scales yet. So you're just really stretching these. You guys yet? Your stretching scale. Here, maybe I'll use this one. So there's some application force to stretch it so much in addition to its original length. Okay. So let's say you use F equals K N. Okay. Here, I'll do the brown scale with you guys. Brown scale. Okay, so it stretches. Ooh, I feel it takes some force. In fact, the more force I put on it, the more it stretches. Or the more I want it to stretch, the more force I have to apply. How do you think of that? Okay. Let's say I stretch this all the, let's say I max this out at 10 newtons, because doesn't the Brown scale go up to 10 newtons? Okay. Now, what is that in comparison to where it started? Like right now, see it's sitting at 0 newtons. There's some original length. Okay. And then if I stretch it to the 10 newton mark, so I'm putting 10 newtons of force to stretch it. Okay. Guys, do I care about the full length of the spring, or do I only care about the amount additional that I stretch it? Yeah, this right here, just the additional stretch amount. And if I hold my roller against it, there's a bunch of rollers all over this last string. That looks about 5.2 centimeters. You have to 5.2 centimeters, right? To max out the Brown scale. Okay. So for F equals Kx, let's see, I want to know K. Right. I know what F and X are. Could you rearrange this to get K equals F over X? That would be in terms of variables. So for the Brown scale, K Brown, the force went to 10 newtons, or to 2 newtons of force to stretch it 5.2 centimeters. Okay. Now, if you divide that up in your calculator, that could give you a spring constant. That would be in newtons per centimeter. Conventionally, these are written in newtons per meter. So let's do one more step here. Yeah. Oh, look, I got some railroad tracks. Railroad tracks. Railroad track. How many centimeters are in 1 meter? 100. Ah, okay. So if I want to convert this to newtons per meter, does the number 100 go on top or on bottom? Yeah, on top. 100 centimeters, or equivalent to 1 meter, gives me newtons per meter. So let's try this out in the calculator. What's 10 times 100? 10 times 100 divided by 5.2. This would be 192, and the unit is newton per meter. Okay, you guys said 192 newton per meter. Okay. So next to Brown scale spring constant, all right, 192 newtons per meter. You guys can't too because I think all the Brown scales are the same. Okay. Okay, so everybody has the Brown scale. Okay. All right, so one of your tasks, before the weekend, so plenty of time, is to find the other 5 scales and figure out what's the spring constant for the other 5. Again, these should all be in order. Okay. All right, guys good? The other lab activity for you guys is you guys gonna build this right here. Okay, so here, tell you guys the concept. We'll show you guys part of a short video, and then show you guys what's going on this page. Okay. So there's the question.
Can I actually see the back of that other map? I didn't get all the information. The thing that we just did, I didn't get all the information.
You think I remember all this?
Thank you, Mr. Griffin.
Right, so what's going on here is we're trying to figure out the optimal location to put this factory. Maybe there's some inputs. Maybe I'm get some lumber from this forest. Maybe I'm get some copper from this mine. Maybe I'm creating pencils, and I'm shipping all the pencils to this town over here. But maybe each one of these has different transportation costs. Right, so this, and this. Suppose, for example, what if it was really, really expensive to transport the lumber for some reason? It's kind of hard to work with it, and it's heavy. We shake down a bunch of it anyway. But maybe it's relatively easy to ship the pencils or get the metal or whatever. If it's really expensive, if it's relatively expensive to transport the lumber, do you want to have your factory very close to the forest or very far away from the forest? Yeah, let's go very close, right? Right, which leads us to there's actually a physics solution to this question, and that's to make the to just hang weights over the edge, right? So you hang over these pulleys right here. Some pulleys with some string. And the weights could be directly proportional to the transportation cost. So that's what they would represent. You guys get that idea? Right? And then if you have a really heavy weight, you guys got all boxes of lab weights here. Right? So maybe this costs like this much to ship it. This is like this, and then maybe this guy's like this guy over here. Okay? And then you can set these up. They can hang down. Right? So here's your weight. Boom, boom, boom. Okay? And then where all the strings are tied together, there's a knot right in the middle. That will naturally be the equilibrium point. I'll tell you exactly where to set it up. You guys get that? Okay. So I do want you guys to see some motion. Yesterday on Google Classroom, I posted this video. Oh, look at that. You guys see a map. You guys see a factory. You guys see, well, now here they have holes drilled through the table, but you guys can hang these over the table, right? Right, so what's this look like from the side or from the top? All right. Find some. All right. Here's, all right. Some of these places say they change out the weight. Here's the guy. You're Varignon. All right, so we talked about the theory of the first few minutes. All right, there's the table. I want to find a place where they hang the weights and it shifts around a little bit. Okay, how about about here? Here we go. Ah, you guys see it? You guys see it? Right, so the factory is there, but if that becomes more expensive on the right, you want to move the factory over to the right. You see it? All right, and then back to table surface. Yeah, so you change out the transportation costs and the equilibrium location of the factory will naturally shift around the map. Right? All right, so that's the other thing you guys do. Right. Okay, you guys good with the concept so far? John? All right, so what does that mean for for this table? Right, so this could be the lab table back there. Right, see, I got three strings. Right, so these could represent three paths. One is to, say, a forest, one's to a copper mine, and one's to a town. You guys get that? Now, the first example here is really just that. It's just an example. So I gave you guys some locations and some corresponding transportation costs. So if you have these going on, like $100 per kilometer, maybe I could represent that with 100-gram lab mass. And they would all be the same. Okay, so set up a probably not too hard to figure out just mathematically, but it would be. Right? And then the second example, I suggested some transportation costs. So if this really doesn't work or you want to make up your own, you could scratch these out and make up your own. That's okay. Okay. But see what's the equilibrium point. And the third one is completely open. Yeah, third one's completely open. Okay. So you can make up whatever sets of transportation costs you want. So wherever you take these pulleys, there's some masking tape back here where you take the pulleys that can represent these locations. Okay. And then there's a little bit of math here, a little bit of trigonometry. So say is one of these forces represent the tensions? And suppose I have 100 grams over here. Guys, 100 grams weighs how many newtons about? About 1 Newton. About 1 Newton. So I just call it 1 Newton. How about 200 grams? Could that be 2 newtons weight? What about 500 grams? Is that about 5 newtons weight? Okay. Which would also represent the corresponding tension from the strings. Then you could take a protractor. You can measure these angles. Got alpha, beta, and theta going on. Now I have them from the x-axis. So maybe pick an axis and measure what's the angle relative. Then you can find some components. So this one over here is pulling left and up. So this one over here is pulling right and up. Okay. And this one over here is pulling a little bit left and a lot down. Okay, you guys see that? Okay. Now, you guys know about equilibrium. You guys solve some puzzles that look kind of like this. Okay? Because let's start with the left and right. You guys see this one pulling pretty far to the left? This one's pulling even more to the right. This one's pulling a little bit to the left. So if you add up a lot to the left, a little to the left, and a lot more to the right, what should the forces sum to on the horizontal axis? 0. Okay, so see if that's true. So this box ideally should be 0 if you do this all right. Okay. The setup, the measurements with the trigonometry, the sign, the plus or minus. All right. Then how about along the y-axis? You guys see this one's pulling up a medium amount, this one's pulling up a little bit, this one's pulling down a lot. Okay. But what does that all sum to in the vertical direction? Should be 0, right? Okay, so see if you can get that. Okay. Is there any question right now? Any question? All right, so you guys got today and tomorrow. You guys got a spring scale lab. You guys got a Varignon frame. And if you finish early, you can work on your take-home quiz, which is due on Monday. Okay. I will walk around and help you guys out.
Yeah, okay.